All right, everyone. Welcome to another lesson in chemistry. Today's topic is lesson 9, the VSEPR theory. So get out your study guides and turn to lesson 9 and let's get started. All right, lesson 9, VSEPR theory. Now, the VSEPR theory, we're going to investigate the various geometric shapes of molecules. Now, remember something very important. Compounds, molecules are not flat. They are three-dimensional. So they do have and take on a three-dimensional geometrical shape. And so that's what we're going to focus on is how to predict, using the VSEPR theory, the three-dimensional shapes of various molecules. Okay, so here we go. All right, so what does VSEPR stand for in the first place? Well, it stands for valence shell electron pair repulsion. Okay, valence shell electron pair repulsion. Now, just as the name implies, it gives us key information into the insights of how to predict molecular geometry of molecules. Okay, so as the name implies, we are going to be looking at the repulsion of the bonding electrons in the valence shell, or in other words, pairs of electrons in the valence shell and how they are going to be repelling one another. Okay. All right. Before we can get any further into VSEPR theory, I need to introduce to you the idea of electron domains. Okay. Now, it's a simple concept. Okay. Essentially, an electron domain is the number, the total number of bonding pairs and lone pairs around a central atom. And it has to be around a central atom, okay? And they do include the lone pairs, and they do include any bonding pairs, all right? So for instance, if you look at this molecular geometry shaped molecule, right? The red here is the central atom, bonded to two other atoms indicated here. Here's the covalent bonds. There's one, and then there's two. And then we have some lone pairs. We have a lone pair there and a lone pair there. So how many electron domains does this particular molecule have? Well, let's count. Each bonding pair, or in other words, each covalent bond is a electron domain. So we have one electron domain, we have two electron domains, then the lone pairs are domains, so that's three, and then finally four. So what we would say is that this molecule has four electron domains around the central atom, okay? Now, I want to make it clear on something else. Let's say we have a molecule that has a double bond, like to this oxygen here, and it's also making single covalent bonds with hydrogens, okay? So this oxygen would have some lone pairs like so, okay? But the central atom is right here, right? This is our central atom, this carbon, okay? So the question is, how many domains or electron domains are around the central atom? So definitely the single bond, which is a bonding pair, is going to be one domain. And this is also a second domain. So far we have two domains. But what about this double bond? Okay. So what we're going to do is consider a double bond as one domain. So we're not going to separate a double bond into two domains. we're going to keep it all as one domain. And that also goes with the triple bond. If we have a triple bond, it is also only going to be counted as one domain. So in reality, we have essentially 3 domains in this molecule. So 4 domains over here and 3 domains here. These lone pairs, because they're not around the central atom, do not count as domains. They have to be around the central atom. Okay, that's really important in predicting the molecular geometry of these molecules. Okay. All right, now we're going to look at 3 key ideas in predicting the molecular geometry and keeping in mind those electron domains. So number 1 is that we need to count the number of electron domains around that central atom. So that's the first thing we do. And of course, those include the bonding and the lone pairs. Okay, we're going to treat, as I mentioned before, double and triple bonds as if they were a single domain. Okay. Number 2, super important. We are going to take and realize that those electron domains are going to repel one another. All right. So any electron domain around the central atom wants to be as far away from each other as possible. All right. So what we need to do is spread out the domains at large enough angles to create a separation of those domains as far away from each other as possible. Okay. By doing that, by separating those domains so they're as far apart, we're going to create the correct molecular geometry. The third thing that's really important is to understand that lone pairs require more space than bonding pairs, which means essentially that the lone pairs have a stronger repulsion that's occurring. All right. So essentially, if you have a lone pair, it's going to cause a bonding pair to actually get closer than it would actually want. And that is because the lone pair is going to dominate. And the lone pair is going to take as much space as it needs to, and therefore causing the domains to push closer to each other. So for instance, let's say you had 2 domains that are bonding, and they're kind of parallel to each other. So here's our central atom, and you have one here and one here domain. These 2 are going to be about 180 degrees from each other. But if you had a lone pair up here, pretend there's a lone pair, my head's a lone pair, okay? That lone pair needs more space to spread out, okay? Which is going to cause these 2 domains to actually bend closer to each other and away from the lone pair, okay? Is essentially what we're looking at here. All right, so super important to understand these 3 key ideas in predicting molecular geometry, okay? So let's do this. Let's start looking at the geometries and start making some predictions here. So the first molecule that we're going to look at, if we count the number of domains, there's only going to be 2 domains. 1 domain here and 2 domains there, okay? This is our central atom in red, all right? Now, because of 2 domains, those 2 domains want to get as far away from each other as possible, remember? So what is the maximum angle that those 2 domains could get away from each other? Well, 180 degrees. So this angle, let me actually clear these domains out. This angle right here from this bond to this bond is going to be 180 degrees, okay? As a result, it's going to get us a linear shape. So any molecule with 2 domains, and those 2 domains are 180 degrees from each other, is going to have a linear geometrical shape, and we'll call it a geometrical shape linear. Now, I want to mention something. You're going to have to memorize this, okay? You're going to have to memorize all of these geometrical shapes. There's no way around it, okay? You're also going to have to know the bond angles in between the domains, okay? So that will be in bonding domains, essentially what we're looking at here. All right, an example of a linear molecule would be like carbon dioxide. Got to sneeze. Excuse me, sorry about that. All right, carbon dioxide, if we draw the Lewis structure for it, is going to look like this. All right, so the double bonds are going to act as one domain, right? So we have one domain here, and it is a bonding domain, and we have a second domain here where these two double bonds are, okay? So essentially we have two domains. The furthest these two domains can be from each other is 180 degrees. So therefore, carbon dioxide is a linear molecule, or has a linear geometrical shape to itself, okay? So there's a good example. All right, let's move on. All right, so now we have two geometries in front of us. One is a trigonal planar and the other one is bent, okay? So let's count the domains first on this first one, this trigonal planar. And we have one domain, two domains, and three domains, okay? And all of these three domains are both bonding domains, okay? So the maximum distance that these domains can be from one another, so the angle, in other words, from here to there is 120 degrees. And you probably could have guessed that, right? You have three angles. What's the furthest they can get away from each other is 120 degrees, okay? If we have a structure, a molecule that has 120 degree angles with three domains, we call that a trigonal planar, all right? An example would be something like, let's say we have boron tetrachloride, where we have a chlorine and then another chlorine and another chlorine, okay? And of course, these are, if I draw the Lewis structure correctly, we're going to have lone pairs on each one of these chlorines, like so. Okay, so there's three domains, 1, 2, 3 domains around boron. Remember, boron only needs 6 electrons to fill its outer shell. So it violates the octet rule, and that's okay, all right? So in this case, these angles are going to be 120 degrees, and we have a trigonal planar structure, okay? So let's go to the second one. Now, the second one also has three domains. One domain, the lone pair is now a domain, and the third domain. So we have three domains, but it has a different shape. Why? Well, it's because of those lone pairs. Remember, those lone pairs require more space. So what it's going to do is it's going to push these two bonding pairs closer to each other. And so as a result, the angle here between these two bonds is really 117 degrees, okay? So they would be 120, but because the lone pairs are going to push them closer, it's going to shrink that angle just slightly down to 120. And so therefore we call it a bend or V-shaped molecule in that situation. An example would be like sulfur double bonded to an oxygen, some lone pairs, and another single bond to an oxygen, some lone pairs, and then you have a lone pair sitting here up here on that sulfur, okay? Because of that lone pair is going to force these two bonding domains to get closer, and therefore they're going to be at 117 degrees from one another, okay? And therefore we have a bent shape that occurs here, okay? There's that. Again, you're just going to have to memorize these. All right, so now we have 3 geometrical shapes in front of us: a tetrahedral, a trigonal pyramidal, and a bent shape, okay? So let's start with the tetrahedral first, okay? So how many bonding domains do we have? Well, we have 1, 2, 3, 4. So there's 4 domains around the central atom of this tetrahedral. What is the furthest that we could get those 4 bonding domains away from one another? Now, you might first think it's 90 degrees, all right? But you would be wrong. They're not 90-degree angles, all right? Because these are 3-dimensional structures. We can arrange those to be even further away than 90 degrees. The real angles in these tetrahedrals is 109.5 degrees. So really the distance, the angle distance from this bonding domain to this bonding domain is 109.5 degrees, and that includes all of the domains around it. As a result, we get what is called a tetrahedral shape, okay? Something that would be a tetrahedral shape would be like methane gas, which looks like sort of like this. If I had to draw the structure of it, okay, as best I can. So the angle here is 109.5 degrees, okay? Tetrahedral. All right, now, next one is a trigonal pyramidal. We still have 4 domains, right? 1, 2, 3, 4, but one of them is a lone pair. So what is those lone pairs going to do to these bonds, the angles between these bonds? Well, it's going to get them smaller. How much smaller? Well, it's going to go from the 109.5 to 107 degrees, okay? So 107-degree angles. As a result, we get a trigonal pyramidal, okay? A trigonal pyramidal. An example of a trigonal pyramidal would be like ammonia. Ammonia has a Lewis structure that looks like this. All right. Now notice these bonding domains are at a very small, or pushed angle here, because this area up here needs a lot of space or a lot of room. So we really have 177-degree angles between these bonds. Okay. By the way, we do not worry about the bond angle between a lone pair and a bonding pair. So we don't deal with angles there. Only angles between actual bonds or bonding pairs, okay? So there is a trigonal pyramidal. All right, now let's go to our last one. Oh, we have another bent or V shape here. All right, this is a little different. It has 4 domains. The other bent one had 3 domains, okay? This one actually has 4 domains, lone pairs being, this is a domain, the other domain, 3rd and 4 domains, okay? So we have 4 domains, just like the other 2 here on this page, but they're lone pairs. And so those lone pairs are going to shrink this angle greatly, okay, down to 105 degrees now. So we've gone all the way from 109 to 105-degree angles, okay, to give us a new bent shape. A great example is water. This is something that everyone should know, that water has a bent shape. Because of that bent shape of water, it has big consequences, as we'll learn later. Okay, so there's my lone pairs on water. These lone pairs are going to cause this bond to get smaller to 105 degrees. Okay, so there's a second bent shape. All right, so just make sure you know the difference between the two bends. All right, so what we've done is we've looked at all of the most common geometrical shapes at this point that we'll find in nature. So most molecules are either linear, either planar, will either be tetrahedral, trigonal, pyramidal, or bent, okay, in most situations. However, there are some odd shapes that occur with some molecules that are made that have what we call the extended octet rule. And based on the extended octet rule, some of these molecules are going to have some interesting geometrical shapes. Okay, so we're going to look at them now. All right, so all the ones that you're going to see in front of us are going to be 5 domains. Okay, and they all have different shapes because some of them are bonding domains and some of them are lone pairs. So if we look at the first one, and again, all of these are going to violate the octet rule, okay? So all of these, trigonal, bipyramidal, seesaw, T-shape, and linear, and this is a different linear, they're all going to violate the octet rule, every one of them, okay? As you can see, you're going to have 2, 4, 6, 8, 10 electrons around each one of these central atoms, okay? So for trigonal bipyramidal, it's going to have a angle that's going to go right here, and that's going to be a 90-degree angle from these two bonding domains. And this is also 90 degrees right here. But you're going to have another one here, here, and around here, and that angle is 120-degree angles. Okay, so now we have, for the first time, a molecular shape that has multiple angles. In fact, it has one more angle because from this bonding domain to the one on the bottom is also going to have an angle of 180 degrees. Okay, so this is a tough one. This trigonal bipyramidal, not only does it have an extended octet, violating the octet rule, but it also has 3 angles that you're going to have to worry about. Okay, what's an example? Let's say phosphorus. Phosphorus can have extended octets, right? So let's say phosphorus is going to bond to some chlorines, and this could be a possible structure, like so, right? And so you got 1, 2, 3, 4, 5 domains. This one is 100. Oh, sorry, my bad. All right, this is 90 degrees, sorry. It's a 90-degree angle. This right here is the 120-degree angle. And then finally, we have from here to there, right, is a 180-degree angle, okay? So there's your trigonal bipyramidal. Now, seesaw, the only difference is we take off one bonding pair, we have a lone pair. And so what's going to do is, first of all, there's going to be no angle here between this bonding pair and the lone pair, okay? But there will be an angle here. Instead of 120 degrees, that lone pair is going to cause that angle to get smaller to 117 for that seesaw. And then from here to there, right, is 180 still, okay, for the seesaw. And you could think the seesaw, you got a phosphorus bonded to a chlorine, bonded to another chlorine here, to a second chlorine, and then we have a chlorine down here, okay? And then we have a lone pair that's sticking up there, and it creates this seesaw structural look, okay? So essentially, again, this angle is 117, and then the other angle from there to there is 180, okay? And then we get our T-shape. Our T-shape has 2 lone pairs now. It still has the 5 bonding domains, but 2 of them are essentially lone pairs. So what's the angle that we can have here is actually 90 degrees. So that's 90 degrees. And then from this one to this one is still 180 degrees there. Okay, so an example might be, and actually it really does look like a T, as you can see from here to there is a T. So like we could have a phosphorus and bonded to the chlorines again, another chlorine, and then another chlorine, and we get our T, right? Here's our T, and then there's our lone pairs right here. So again, this one angle is 90 degrees, and then from here to there is 180, okay? And then finally, we get another linear shape because we only now have 2 bonding domains and the rest are lone pairs. So the maximum that we can have is 180 degrees, right? Because these are our 2, so there's our lone pairs. So from here to there, it's got to be 180 degrees. And anything 180 degrees is going to be a straight line or linear, okay? So from here to there is 180 degree angles, okay? There we go. Okay, so those are all the 5 domain shapes that are possible, okay? So we have one more series of shapes, okay? Well, yes, one more series. These all have 6 bonding domains, yes, or 6 domains in general, okay? But there's only 3 shapes, and the angles are super easy because all the angles are the same here, okay? So the first one is an octahedral. 6 domains, let's count them, 1, 2, 3, 4, 5, 6. And the maximum we can get is 90 degrees. So these are all going to be 90 degree angles all the way around, okay? An example is sulfur. Sulfur can have an extended octet. So all of these are going to have extended octets, obviously. So sulfur can have an extended octet. Let's say it's bonded to a fluorine. And then it's going to have another fluorine, and another fluorine, and then another one. Okay, and then a fluorine off this way, and a fluorine off this way, essentially. Okay, and really, these 2 fluorines are kind of sticking, as you can see, one sticking out towards you, one sticking in the back, and so these are all going to be 90 degree angles there. Okay, so there's an octahedral. A square pyramidal is just one of the bonding domains is now a lone pair. Okay, the angles are still going to be 90. So that's what's awesome about all of these 6 domains. If you see 6 domains, all the angles are going to be 90 all the time. Okay, so here all we're going to have is sulfur bonded to a fluorine, and then we have that one, this fluorine, okay, and then we have essentially fluorine coming out this way, fluorine coming out this way, and then we have our lone pair right there, lone pair, okay? So the angle here is still 90. And then finally, a square planar, we have 2 lone pairs now, and really, again, the angle here is going to be 90. They're all going to be 90 degree angles. So it would look like literally kind of like a square where you have these like so, and then you have lone pairs like this, okay? So you kind of create the square that's flat, a planar structure flat, all right? So, and again, 90 degree angles for those square planars, okay? So there we are, 6 domains, and we're good to go, okay? All right, so let's go back. Oops, I'm not doing that one yet. Let's go back to the beginning here, and let me show you some models, okay? So the first one is linear, and this is what a linear molecule might look like. Okay, here's carbon dioxide that I showed you. Here's the two bonding domains here. And notice it creates a linear shape, okay, to it. Okay, so linear 180-degree angle. Okay. A planar, something like this. Here's a model of a planar. Here's our central atom right here, and our other atoms forming our three bonding domains. And again, the maximum that we can get here is 120-degree angles all the way around. Okay, 120-degree. We have a planar. Notice it looks flat, and it's a triangle, so we call it a trigonal, triangular, sometimes a triangular planar. Okay, it's flat as a plane and has a triangle shape to it. Triangle. Okay. All right, a bent. Okay, something like this where it's bent. It does have two lone pairs that are not indicated here, but you got to visualize a lone pair here, up here, causing this to be bent down to 117-degree angle. Okay. Let's go to our four domains. So we have, let me show you a tetrahedral. This is what it would look like, 109.5-degree angles. This is methane. So all of these angles are 109.5. You see this nice tetrahedral, three-dimensional shape here. Tetrahedrals are very common geometrical shapes in nature. Okay, tetrahedral. All right, and then we have our trigonal pyramidal. Okay. First of all, the reason why we call it a trigonal pyramidal is because it looks like a triangle here on this side, 1, 2, 3, but it also has a pyramidal shape. If I put this in my hand, it kind of has that pyramid look to it. Okay, so we call it a trigonal pyramidal. It has a lone pair setting up here. Okay. And the angle, therefore, because of that lone pair that sets up there, is going to push these angles close together. So instead of being 109.5, they're going to be 117, right? Or sorry, 107-degree angles. Okay. Okay. And then we got bent again. The only difference between this bent and the other one is now we have two lone pairs, right? So we have a lone pair here and here. So it's going to push that angle even closer, and it's going to go down to 105-degree angle. So this is like what water would look like, okay, or a model of water. Okay. All right, now let's go to our trigonal bipyramidal. So here's a model of a trigonal bipyramidal. Okay. So our central atom and then our other atoms bonded around it, okay? So first of all, remember we have three different angles. This angle from here to here, or from here to here, or here to here, those are all 90 degrees, okay? The angle from here to here, though, this angle is 120. So 120, 120 as they spin this around, okay? So 120-degree bonding angles there. And then finally, from here to there is a 180-degree bonding angle, okay? 108. Okay, so this is your trigonal pyramidal shape, okay? So to be familiar with. Okay, now if I take one of these off, now I have a seesaw. And right here is our lone pair. So there's a lone pair sticking right here. And so it creates this seesaw shaped. I like to kind of think of a teeter-totter almost, where you have two legs out here and then holding up this section here, kind of creating the seesaw or teeter-totter, okay? And now this angle here to here is 180 degrees. And because of this lone pair here, it's going to push these together to create a smaller angle of 117. Okay, so instead of 120, it'd be 117 from here to there. Okay, once we do that. And then finally, we get our T shape. T-shaped here, it looks like a T. We have a lone pair back here and a lone pair here where these holes are, okay? So it creates that T shape, and therefore it results in essentially 90-degree angles here and here, 90 degrees here and here. So from here to there, okay? T shape. And then linear, I now have 3 lone pairs, one here, and one here, okay? And that creates this linear shaped molecule or 180-degree angle, okay? So there's our 5 domains. So we have 6 domains left. Let me show you the models of those. And we're almost done here. All right. So our 6 domains. So this is an octahedral. Okay, it has 6 domains around it. Okay, it has really, because of the faces, it would create an octahedral look to it. So that's why it's called octahedral. 90 degrees all the way around. So it's really easy. Remember, any molecule that has 6 domains around the central atom is 90-degree angles. Okay, we take one off. We have a lone pair down here now, and we have our square pyramidal. Okay, and that the square, it looks like a square, right? But it also has a pyramid shape to it. If you look at this, is the pyramid point, and it's going to have these pyramid look to it. Okay, you have to use your imagination a little bit. And again, these are 90-degree angles for the square pyramidal. Square, right? Square, you can see the square, hopefully. Square around it, and then the pyramid, okay? And then if I take off another, and I get a square planar, and that should make sense because it looks like a square and it is flat. So square planar with the 2 lone pairs, but these are going to create 90-degree angles, okay? So they'll still stay 90 degrees, all right? So there's all of the molecular shapes that you need to know for the test, essentially. So I've given you some examples, I've given you the names, I've given you the angles, I showed you some models. You might need to go back and review this a lot, but you're going to have to memorize all of these shapes and angles. And then once you draw a Lewis structure, in fact is that's where I would begin, is drawing the Lewis structure. And once you have a Lewis structure, then put those domains as far away from each other as possible. And then from there, you can predict the geometrical shape. And that's where you should start, okay? So let's do one last thing. What if you have some kind of a molecule that has multiple central atoms, okay? How do you predict the geometry there? Okay, so for instance, we have one central atom. Notice that this oxygen is a central atom to this carbon and this hydrogen. It also has lone pairs on it that I'm going to place there, okay? And then you have this carbon, which itself is a central atom. This surrounded by this oxygen, this second oxygen, which also has lone pairs, and then this carbon, okay? So this right here, let's say, is a central atom. This right here is a central atom, okay? But we also have this central atom here, all right, as well. Okay, so we have, let's number these, or let's give them a letter. So central atom A, B, and C. So how are we going to determine the geometry of this molecule if we have 3 separate central atoms? Well, the answer is very easily. You have to name all 3 geometrical shapes. And you have to identify each geometrical shape around each central atom. All right, that's as best you're going to be able to do here. So let's look at A first. What does A look like? Well, first of all, it has how many domains? Well, it has 1, 2, 3, 4 domains. So this A central atom has 4 domains. They're all bonding domains. So the biggest angle that we can make is 109.5 degrees. So we would say that the geometry around central atom A is a tetrahedral shape, okay? Tetrahedral shape. So then we go to B. Well, B has how many domains? Well, it has one domain here, has a domain here with these double bonds, and another domain there. So it has 3 bonding domains. Well, what's the maximum angle that we can get with 3 bonding domains? 120 degrees. So what shape has 120 degree angles? Would be a trigonal planar shape, right? It's a planar. Okay, that's the geometry around the central atom B. Okay, and then finally, C. Well, we have 2 domains that are bonding, right? This and this are 2 domains. And then we have some lone pairs. Lights went out. Okay, and we have 2 lone pairs. So we have 4 domains, but 2 of them are lone pairs. So what shape does that give us? Well, it gives us a bent shape of 105 degree angles. Okay, so we essentially got a bent there. Now, if we put this all together, I actually have a model of it. It's going to look like this. Okay, so here's our model. All right, this is the central atom right here, A. Okay, notice it has its tetrahedral shape to it. Okay, there's that central atom, tetrahedral 109.5. Then we have this central atom right here, this one, and this is going to be a planar because it has 1, 2, 3 domains, and those 3 domains are creating a flat surface. If you can see that, it's a flat surface. It's a trigonal planar structure here. And then finally, we have our bent. This is our 3rd central atom, and we have a flat, a bent structure here with a 105 degree angle right here. Okay, so when you have multiple central atoms, a more complex molecule like this, then you will have to essentially count each of the central atoms and do the geometry for each one. Okay, and there you have it. All right, so that's it for this lesson on VSEPR theory. That's all I'm going to mention at this point. We will expand on the VSEPR theory with Lewis dot structures and other various things here later. But that's it for lesson 9. Study hard, and we'll see you later.